In this video, I'll discuss the kinematics of projectile motion. We start with the figure shown. A projectile begins its motion with an initial velocity v sub 0 and is projected with an initial launch angle theta. As the object rises, its velocity vector can be broken up into its x component and its y component. Its x component is horizontal and never changes, and its y component is either up vertically or down vertically. On its way up, then it's up vertically, as shown. And the projectile continues to rise along this parabolic path until it reaches the top of the path, at which point the y component of his velocity goes to 0, but its x component remains the same throughout. And then on its way down, the y component is always pointing downward, growing as it goes downward. So it's negative, and once again the x component is the same, pointing to the right at that constant amount, v sub x. We should point out that we know from the trigonometry of the initial velocity and the launch angle that the x component, v sub ox, which is the same throughout, v sub x, is equal to the initial velocity times the cosine of the launch angle. And the initial velocity in the y direction, that is the y component of the initial velocity, is equal to v sub o times the sine of the launch angle. So now we're ready to describe the kinematics. And when we do, we can break the kinematics up into the y component kinematics and the x component kinematics. So we have our four equations, kinematic equations with constant acceleration, since the acceleration throughout the projectile's motion is a sub y equal to minus g. And we note that in the x direction there is no acceleration. Then we write our four equations. Our first equation is the final velocity in the y direction is equal to the initial velocity in the y direction plus the acceleration times the time. So we write that as minus g times the time, and we label that equation 1. Our second equation is change in y, or the displacement in y, is equal to v sub o yt minus 1/2 gt squared. That's equation 2. Equation 3 is the final velocity in the y direction squared is equal to the initial velocity in the y direction. Let me correct that. Write it this way. The final velocity in the y direction squared is equal to the initial velocity in the y direction squared plus 2 times the acceleration times the displacement. So that's minus 2g times the displacement in y. And then for equation 3, the displacement in y is equal to the average velocity, which is the sum of v sub y final plus the initial y divided by 2 times the time interval t. There, that's better. Now, I should stress that whenever you use any one of these four equations, when you evaluate v sub y, you should use this expression, v sub y is equal to v sub o times the sine of theta. A common mistake that is made is to forget to do that and instead to use v sub o instead of v sub y. All right, how about the motion in the x direction, the x kinematics? Well, as I already said, the velocity stays the same throughout, and so the displacement in x is just equal to v sub ox, which is equal to v sub x times the elapsed time t. So I can call that equation 5 if I want. All right, good. So now we can solve any part of a projectile problem using these four equations for the y kinematics and the one equation for the x kinematics, knowing that the t, the elapsed time, is the same in each set of equations. So we can always use information from one set and apply it to the other set. All right. Now there's only one other thing I want to talk about in this discussion, and that is how to solve for time when you're in a situation such as when you must solve for the time and you are perhaps feel that you're forced to use equation 2, which is solving this quadratic equation of time. And as I've said in both of my recitations, a simple way is to use the combination of equations 1 and 3 to get a final expression for t, which avoids having to work out the quadratic equation solution. So the starting point is to use equation 1 and to remember that equation 1 comes from the fact that the instantaneous acceleration in the y direction is equal to the average acceleration, and the average acceleration is equal to v final y minus v initial y divided by the time. So from that we see that the time is equal to v final y minus v initial y over the acceleration in the y direction. And since the acceleration in the y direction is equal to minus g, then we rewrite the equation as v sub oy minus v sub fy over g, where we replaced a sub y with minus g, and then multiplied the numerator and the denominator by minus 1. Okay. Now we're ready to use our equation 3. And we use our equation 3 here to solve for v sub f y. So we have v sub o y minus, and I'm going to put this in parentheses because this is an easy way to mess up if you don't, minus plus and minus the square root of v sub oy squared minus 2g times the displacement in y. And I divide all that by g. Okay, so now when do you use the plus solution and when do you use the minus solution in this, inside this parenthesis here? Remembering that the quantity inside the parenthesis is equal to the final velocity. Well, you want to use the plus solution when v sub fy should be positive. That is, when the object is on its way up. And you want to use the negative solution for when it's on its way down. So when it's on the way up, inside the parentheses, you want to use the positive solution. So we have a negative times a positive, which is a negative, which means that the time is equal to the initial velocity in the y direction minus the square root of v sub oy squared minus 2g times the displacement in y all over g. And when it's on its way up and when it's on its way down, we're going to have a positive solution because we're going inside the parentheses, we're going to use the negative solution, and then we have a negative times a negative, which is a positive. So then our elapsed time is going to be equal to v sub oy plus the square root of v sub o, v sub o y squared minus 2g times the displacement of y all over g. And that concludes this video.